So I'm going to go ahead and write these out. Other than that, we got the same name. We got an extra hyphen in there for our tert, which should actually show up. You should see that hyphen. So drawing it up on the board, we want to identify our main chain. Our ring has the most number of carbons. How many carbons are in there? 6. So we have cyclohexane. Can then look at our substituents. We've got methyl and methyl. And then we also have this funky looking group. Okay. Hopefully you got that roughly memorized from the previous slide or previous couple slides, and you can see that as tert-butyl, or you might see it as just T-butyl. Okay. It doesn't have to be written out as tert-butyl. Where are those carbons located, or those substituents located? Our tert-butyl, again, having our higher priority. 1 T-butyl. Our methyls, and you guys numbered it correctly. We should number clockwise in this case. Remember, it's specific to the case. We'll end up with our 2 and our 4. When we put the name together, we've got it correctly written out here, so I'm going to write it down underneath. We could write it as 1 T-butyl, 2,4-dimethyl cyclohexane. You guys had both of those, yes. Why did you put the T-butyl first? Doesn't T come after M?
Priority. It's butyl.
Not when you put it into a name. That's the numbering, gives you the priority for 1. When you put it into the name, it's alphabetical. Why did T-butyl come first? Because it's butyl, not because it's tert. You still have the proper sequencing. It really is 1 T-butyl.
That's why I did it. That's exactly why I did it.
1 T-butyl, and then we have our 2,4 dimethyl cyclohexane. What if it had been isopropyl? Does it get sorted because of the iso or the propyl? The propyl. Is it? Oh man, this is why I don't like our nomenclature. I'm pretty sure it goes based off of the propyl, but I could easily be wrong on that. The book said iso, then it goes based on the iso.
So then shouldn't we have gone based off the tert in this case?
Tert definitely doesn't take priority, for
Okay.
sure.
Oh, because it's just classifying it as having 4 carbons.
Yeah. Okay. So you have to be careful with how the names get put together and how you deal with them. It is going to be something that's going to show up within your sapling that you're going to have to watch out for. When it comes to the ACS test and any question on the exam, they will be shown as multiple choice. So you'll have very limited options as far as what things could go wrong with putting the name together. Okay? Questions about nomenclature?
Iso is the I? Iso?
With the I.
With the I.
Spelled with an I, yeah. Okay. Physical properties. If we're going to look at our alkanes, what would we predict for our melting point or boiling points? High or low? Why would we expect very low melting points? The intermolecular forces are very weak, which comes from which type of bond? Not just single bonds, covalent bonds, non-polar covalent. So we would predict very, very low boiling points. Okay, so if we compare to something else with higher, more intermolecular forces. But what happens in this case? All of these are alkanes. What if you're asked to rank boiling points here? Okay, now we're going to have to come up with some slight tweak to how we're going to approach these. Okay, which one's going to have the lowest boiling point? The one on the left has the lowest. Why does the one on the left have the lowest? C4 versus C5 versus C, it's still C5. Okay, so we have less carbons. Why does that impact this? And yes, someone already said it, has to do with surface area. If we increase the amount of surface area contact, we're now allowing more places for those individual forces to potentially form. Okay? So if we can maximize that surface area, we end up with a higher melting point or boiling point because there's now more places that that weak interaction can occur. When we first considered this, we just looked at which is the strongest interaction and didn't worry about it after that. Now we actually have to take into consideration other structural effects as well. All right, so if we look between C4 and C5, left and middle, our middle one has more surface area, more places to potentially contact. What about that last one? What does the branch do? It's going to take away some of that surface area. It's going to disrupt the neat packing of our overall structure. If we look back to that middle one, I can continue to pack more structures evenly off the top of that and maintain that even interaction. If we take a look at that last one, with that branch sticking in there, it's really going to disrupt how I can pack other molecules on top of it. So when you look at your melting points and boiling points, it is important to go through and evaluate the strength of the intermolecular force, but then you also need to worry about the size of the molecule, which I would equate to the amount of forces. So when you looked at solubility in the lab, methanol versus octanol. So methanol has 1 carbon, octanol has 8 carbons. Which one was more water soluble? The methanol, because we had very little London dispersion interactions. Even though both of them are alcohols, both of them have that hydrogen bonding ability. The octanol has more London dispersion force kind of accumulating for the overall structure, and we end up seeing a significant difference in their solubilities. All right, the last thing that we could look at is branched alkanes typically have lower melting or boiling points than their counterparts. All right, are there exceptions? Absolutely. Hopefully you won't have to worry about the exceptions as much. If it does, an exception does pop up on the test, any ideas how it's going to be presented? I could be really mean and just say, rank these and the exceptions mixed in with that. More than likely, if you're going to hit C exceptions on the test, the way it's going to be phrased is, this is an exception. Explain why it's an exception. Right? So you'll have to look at the structures given and try and interpret how does that exception make sense? Why does it shift away from the natural patterns? Right? Can't think of an exception off the top of my head, so I'd be surprised if you saw one like that on the test. If we look at overall alkane reactions, so we got this nice structure here. What types of bonds do we have? We've got covalent bonds, or nonpolar covalent, which gives us what type of force? London dispersion. What types of interactions are we going to get? Very, very weak ones. We don't have enough polarity to really do much, which means synthetically we have very limited reactivity when it comes to alkanes. So as far as this chapter is concerned, we really don't have anything that we can work with. Okay? It's not 100% true. Chapter 15, we're going to talk about radical chemistry somewhere towards the end of the semester. And if we're going to look at those radical reactions, we're going to be concerned about that carbon-hydrogen bond. All the hydrogens are on the outside of those structures. The hydrogen's going to react first. Okay? We can also go through and do petroleum-based chemistries. Most synthetic chemists aren't going to be dealing with that petroleum-based chemistry because it's too tedious to deal with. Okay? But anybody in a petroleum industry is going to be doing them on a large scale pretty much all the time. So you'll hear a couple phrases come out of that: cracking and combustion. What is cracking? What do you think is going to happen with cracking? What's that? If I give you this compound, and now I say crack it. Break it. So cracking is referring to breaking down larger alkane structures, okay, into smaller pieces. What about combustion? Okay, you're going to react it with oxygen to generate CO2 and water. Synthetically, why is that useless to us? Water we have everywhere. CO2 also everywhere, but take it a step further. Virtually unreactive. Remember, it goes back to that greenhouse issue. Right? We can't get CO2 to react very easily, which is why it's filling up our atmosphere. Okay? So, the rest of this chapter is looking at models, and we've already kind of talked about structure and models a little bit. We're really going to push it to the limits within this chapter and chapter 5. Okay? So, Methane. Is it really necessary to draw out structures in a model for methane? Everybody hopefully fairly confident with that? Okay, so we've got that tetrahedral structure. We oriented it such that we have one wedge bond coming at you. So if we look at a very small version of a model kit, we have effectively our ethane here. We've got two bonds, 3 atoms in the plane of our paper. And then we have one bond coming out towards you and one bond going away. The one coming towards you is marked as a wedge, the one going away, dashed. Okay? And we could go through and you'll see it with the ball model that they've got drawn up there as well. Oh, sneeze. What if we shift to ethane? Maybe it's gone away. Let's not quite look at that yet. If we took a model kit for ethane and tried to draw out our Lewis structure, what would it look like? You're all great with Lewis structures? Right? What if we wanted to show the three-dimensional structure a little bit? So if we took a look at a model of ethane, right? The real model doesn't have all of those hydrogens nicely scattered around, so we might want to try and draw this structure as best we could. Okay? So I'm going to draw the answer for what this looks like in just a second, but feel free to take a look at it and tell me what you see. How would you draw this structure? Okay. And I will, you can just draw it. You don't have to say it out loud. If you want to say it out loud, that's fine too. And if you've got a model kit, now is a good time to bust it out and try and build what I'm holding up. If we went through and tried to draw that, we've got our carbon atoms in the same plane. If you also notice where my hand is holding, that bond is in the same plane as the one to the left, so I can draw an upwards angled bond for both of those. If we're looking at ethane, those would be hydrogens, so we could tag in our hydrogens. Next part of this, since we have a tetrahedral structure, we could just draw our wedges and dashes in here and be happy with it. But again, we want to accurately reflect this as much as possible. Where are the wedge and the dash in this structure? They're both coming towards you and slightly down and kind of away from our carbons. So we would go through and draw in our wedges to represent that. And we could tag in our dash. Again, our dash we're trying to represent as best as possible. You'll notice that where is that bond? It's again going down and a little bit out from the structure. So we're trying to represent that three-dimensional structure as best as possible. All right, if we advance to the next slide, it's going to address a special characteristic of the bond between the two carbons. What type of bond do we have there? Sigma bond. What can the sigma bond do? It can freely rotate. Okay, so hopefully you've got this drawing up here. And what I'm going to go ahead and do is rotate. Try and draw it again. This time I'm going to again try and walk by and give you that opportunity again to attempt to draw it. And I will draw it up on the screen here in just a second. Again, we're trying to reflect the structure as much as accurately possible. Should it be drawn the exact same? There is a slight variation to it. And I'm going to erase that middle one. Actually, I'm just going to erase the back, the right side of it. If we take a look at the left side, we still have our hydrogen going straight up. And we still have a bond coming at you and away from you, all down and away from the structure. So the left side of our drawing is fine. The right side of the structure has changed ever so slightly. Where's the hydrogen, or where's the bond now as far as the plane? It's now aimed down as opposed to up. So the solid line that I'm going to use is now straight down. If you having problems visualizing it, please feel free to give me a dirty look and I'll aim it towards you again. Okay, you aren't giving me enough dirty looks, I'm putting it down. We've got our hydrogen there. What about our wedge and dash bond? Where are they now located? They're now aimed upwards. There's our wedge, and there's our dash. Again, we're just trying to accurately reflect that structure as much as possible. Is there a difference between these two structures? They both represent the exact same compound, but is one conformation of different energy than the other? Turns out, yes. One of these has a characteristically different energy than the other. One is very low in energy relatively, and the other one is very high. Why might that be relevant? It could look at reactivity. It's also going to look at the natural state of that molecule. What is that molecule going to look like when we put it into solution? That's going to change how it can potentially react. To visualize that energy, we need to stop looking at the structure from the side. And what we need to do is actually turn the model. So when you turn it, what we're going to do is hide that back carbon atom. And what we're looking at in this case is the alignment of the bonds. Why should we look at the bonds? All right, let me rotate it real quickly back the other direction. What's the only difference between our two conformations? So there they're both up.
The hydrogen atom is perfectly aligned.
It's where our bonds are located. They're now in the same conformation, or the same alignment. Why is that important?
Maybe some sort of like overlap between.
There's going to be a potential overlap. An overlap of what? Electrons. What happens when electrons get near each other? They repel away from each other. All right, so what they've attempted to show, because I stole it, I didn't say that. What we're trying to show in this image is in that first structure, our hydrogens are overlapping with each other. Those are ultimately in the same plane. That's the model that we've got. Oh, actually, anybody want a model real quickly? Really? Okay, fine. You want one too, Tim? What they're trying to show with the one with the red bonds is this one, where those bonds are all aligned with each other. When we move to the right structure, what we've got is this one. Okay. The difference is that in our rightmost structure, the bonds, the electrons, are now not occupying the same space. What does that mean for stability? Which of these two structures is the most stable, right or left? What happens when you bring electrons near each other? They repel. Which structure has the lowest energy? The right one. We've taken those electron density, or that electron density of the bond in those atoms, and we've put them into their own space where there is nothing else occupying. Right? So our right structure becomes the most stable. How many of you can draw that three-dimensional structure up there right now? The shading.
That's all right.
Takes a little bit of skill and practice to be able to draw these out. So what we want to do is come up with some way to modify it so we don't have to deal with all that shading. So we've got our Lewis structure, which we've seen. We've got the line angle, which I just went through and drew up here again so it doesn't look as messy as my handwriting. And what we want to do is now adjust to that alternate view. Right, that alternate view was, of course, named after someone, the first person to identify it. That person's name was Newman, okay? Which everybody in this class is probably going to learn to hate because these projections take a little bit of practice getting used to seeing and manipulating. That practice and manipulation ultimately comes from having awesome spatial awareness, which I don't, as we've seen me walk into things all the time. Okay? And most people don't have that ability to see with that kind of spatial relativity. So what you would need to do is develop that relativity by playing with the model kits. The model kits help you to see that awareness or that alignment. Yeah. Invent new words all the time. So what we're going to do is take a look at these structures from that end and try and draw that model or draw what we see. Okay? Newman came up with some suggestions in that drawing to simplify it so that we don't have to deal with drawing all the atoms and getting, oh, this one's coming at you, this one's going away, because that becomes very difficult to draw in that case. Remember, all the atoms are overlapping each other, okay, or all the atoms could be overlapping each other. So what we want to do is come up with some kind of simplification of that notation. Okay? So if you attempt to draw that, hopefully what you'll end up getting to is something along these lines. Okay, the leftmost structure matches the leftmost drawing, rightmost, rightmost. Almost. Shucks.
Do you draw them off center like that? Left one so you know that there's something behind?
So if we want to attempt to do this, the one drawn on the left, those bonds completely overlap. Would we be able to see those bonds? No. So what we're going to do is tweak the structure ever so slightly. And instead of looking at it exactly end on, we're going to turn it just a little bit. That slight turning in the structure allows us to better see the bonds so that we can actually draw them out and see all of those atoms. Okay? Next thing to be aware of, okay, because I did the left one 100% correctly. Where is the red carbon in the leftmost drawing? It's got to be the front atom. Where's the front atom in that structure? It is the dot right in the middle. Where is now our blue carbon? It's behind it. It's going to be the circle, which is kind of opposite to what we would expect. Remember, the back atom we don't see anymore. Why did he switch it like this?
So that you know it's there.
If we're going to try and draw on the bonds of all of the hydrogens, okay, would we be able to see where those back hydrogens are connected to? Particularly if we use the circle in front. All we'd see is them come down to the circle, and we'd never see what they were connected to behind. Okay, so we have to do almost a reverse perspective so that we can actually see where those atoms are connected to each other. Okay, without that reverse perspective, we can't see the connections between these. So I'll go through and draw in our hydrogens according to the appropriate colors. And then we've got our red hydrogens for in front, coming out of the point in the center. All right? And if you look really carefully, you can see that in 3D now. Anybody that old? Come on, the red and the blue, right? I guess you need the glasses. If we go through and look at the other drawing, right, it is the correct energy, but it's actually technically the wrong drawing. Why is it the wrong drawing? So let's add some colors to this. Where's our orange carbon? Is it going to be in front or in back of our viewpoint? It's in front, so it should be our dot, right? Where's the hydrogen? It's aimed directly up. Is the Newman projection I've got showing that? No, I switched the perspective on it. I kept going back and forth on these, trying to get it right. Apparently I messed this one up. So let's draw that Newman projection as it should be. Got our hydrogens coming down towards the sides. And we drew on our purple carbon is going to be our circle behind. Okay. So that is the more appropriate Newman projection for that rightmost structure. What's the difference in energy? So now if we take a look at our red-blue versus our purple-orange, our red-blue is going to be higher in energy because the bonds overlap each other. They're in that same axis, that same plane. So what's going to happen is those atoms are going to push away. And as they push away, they're going to start to find a space where eventually it starts to butt into the other atom. So it goes back the other direction. And where we end up settling is our orange-purple drawing. And depending on what we're looking at or our perspective, we might draw it as our orange-purple, exactly as shown in the line angle drawing, which, hint, hint, sapling will make you do this. You have to draw it exactly as they've got shown. Okay? Or you would draw it as shown on the far right. Okay? In this case, does it matter which drawing I show? Not really, because same energy. Okay? So we don't see a big difference in the overall energy. So both of these drawings represent that. What we now want to do is come up with a way to separate these two. Okay? Come up with a name to explain what one is, and come up with another name to explain what the other one is. Okay? What are the names given to these two drawings? We've got the eclipsed conformation. Think about a solar eclipse. Right? The moon is aligning with the sun, right, blocking it out. So what we're looking at on our far left is an eclipsed conformation. And on the right, what we've got is a staggered conformation, because all of the bonds are staggered around each other. I don't know if that's spelled right. Close enough. Okay? Questions about these views? Okay, let's make it more challenging. We're going to skip propane and we're going to move directly into butane. If we drew out the straight chain version of butane, okay, what would you get? Get them all drawn together. We could look at the condensed form, or sorry, I don't even remember what to call that one. Our structural formula versus our condensed formula. You're responsible again for being able to interpret all possible of these drawings. Okay, so now what I want you to do with that model, okay, either in your head or physically in front of you, rotate it so that you're looking down the carbon-2, carbon-3 bond. Okay? For the two of you that have models, I lied, I need it. Okay. Okay, so let's take a look. Theory, you're reasonable with your Lewis structures. If we looked at our Vesper model, we've got kind of the bond angles with our jagged lines, okay, between those. And now what I want you to do is change the orientation, your viewpoint on this structure, so that we are looking down the carbon-2,3 bond. So that bond needs to disappear from view. Right, where is carbon number 2? Okay, there's carbon 2. Where's carbon 3? All right. I want to change the viewpoint of this model such that you are looking down that bond, that carbon 2, carbon 3 bond. So if we take this model and now turn it, you're now looking at down the carbon 2, 3 bond. And what I'm asking you to do is to draw what you see. And you should do it with the Newman method. One caveat, where is our Newman projection? It's based on the carbon-2,3 bond. What atom is this guy? 4. What atom is this guy?
1.
Are either of those atoms in a Newman projection?
No.
Not really. Those are just CH3s that are part of our carbon-2,3 Newman projection. So instead of in our previous structure where we just had hydrogens all the way around, 2 of those hydrogens are going to be exchanged for carbons. Okay? So what you need to draw is exactly what's shown here. Let me remove these bonds, maybe that'll help. Because I don't care about the atoms coming off of the carbon-1, carbon-3 bond, or carbons. All I care about is carbon-2, carbon-3, the bonds coming off of those 2. Draw exactly what you see. And that's exactly what I've got drawn up here too. Anybody have questions? Okay, laughing means I'm going to walk towards you.
Do I have any questions?
So, take a look at what you've got drawn and compare it to the people around you and see what you see what they look like.
That's what he said, because he said they're not any Newman projection.
Specify. So you want to have hydrogen on those things, otherwise we think we're carbon.
I got you. Because, no implied hydrogens in you.
Draw a dot. Just a
Just
single
a
dot in the
dot.
middle of your paper. Where does this happen?
This?
Same thing.
Yeah, no.
I didn't have enough time.
But yeah, it's the same thing. You would just turn that anyway.
How do we specify the atom in bond? What atom is it connected to? Is it connected to the dot, which is the front atom, or the circle, the back atom? So draw your bond to the circle. So because I definitely want to get a little bit further with this, hopefully what you should see or is generate a couple different systems, okay, in comparison to your ethane. We should end up with both a staggered, which is what we initially had on our model kit, and an eclipsed. Should have gotten both of those. You'll notice that our structure is going to change a little bit because I don't have my pen. There it is. Because we're not looking at hydrogens now, we now have carbons. So we could go through and specify, connection, seriously? Yeah, today is a problem. We've got a carbon atom here and a carbon atom here. If we go through the same kind of idea that we were doing before, we go through and rotate around that carbon 2, carbon 3 bond. When we do that rotation, there's our eclipsed conformation. What atoms are eclipsing? A carbon and hydrogen. Let's rotate that to our next eclipsed conformation. What atoms are eclipsing now?
Carbon and carbon.
Carbon and carbon. Is that going to be a different energy?
Yes.
Why? Carbon has more electrons than hydrogen. We end up with different eclipsed interactions. Do we care about the eclipsed interactions? Why not? Because they're ridiculously high in energy. So when we look at our eclipsed interactions, we typically classify them as just eclipsed. Yes, they have varying energies, but we'll never actually form them because they're such high energy. What ends up happening is that we will pause in our staggered conformations. So let's go through and look at our staggered conformations. We've got our initial staggered. There's our eclipse. That's bad. So let's do one more staggered. Is that different? Why is it different? The carbons are closer. If we take a look at what I've got drawn up here, instead of putting on carbons, I put on X groups. Why X? Because it's going to apply to every single possible structure you can imagine. Every single one of them, you could go through and draw out a Newman projection to go through and evaluate those alignments. When we look at reactivity, this term isn't going to mean anything, but in eliminations, the two-type mechanism, we need Newman projections. Okay? Because that's going to determine that that reaction can actually occur. If we take a look at our other one, we've got our carbons aligned in that fashion. Is there a difference in energy? Which one's lower in energy? The one on the right. Oh, that's interesting. It's actually drawn a little bit lower. Yes. Planned that. Okay, apparently you guys aren't as impressed. So we've got our eclipsed conformation. We have our staggered. What happens with our next two? Isn't this drawing still staggered? Yeah. How about this drawing? Still staggered. Right? But they have different energy. They're more staggered. So we need to come up with a new name to represent each of these new structures, these new staggered structures. Okay? As a hint, you can probably pick up the rightmost one as a name first. That's probably the easiest one. Where are the carbons located? Opposite or anti. Okay? That conformation is known as your anti-conformation. Okay? The next one over is a little bit more difficult, but you might be able to get that one figured out. Okay? You see how those carbons are kind of close to each other? I don't know where that one came from either. It's gauche or gauche. I don't know. G. Okay? That's referring to those two groups interacting with each other. Okay? That would be the gauche conformation. Okay? Or this structure is now drawn in our gauche conformation. Let's take it a step further. What type of interaction is between these two blue hydrogens? It's gauche. It's a gauche interaction. Okay, now we're looking at referencing any two atoms and trying to determine their relative energies with each other. What if we go over to the anti-structure, and now I want to look at the interaction between this blue hydrogen and now my blue carbon. What interaction is there? It's gauche. The anti-interaction is when we're looking at our two atoms on complete opposite sides of each other. Okay? So what happens if I now look at, let's call it our orange hydrogen, and this orange hydrogen? What's the interaction there? Anti. Okay? So, oh yeah, good job. Our anti-interactions, okay, the anti-interaction is referring to any two atoms. Okay? Our anti-conformation is referring to the exact conformation where our largest groups are on opposite sides of each other. So we get conformations versus interactions. Questions on that? Okay, let's spin it a little bit graphically. We could go through and actually calculate the different energy levels behind these. It is something that is very common for to show up in a lot of these kind of organic classes. It involves math, so as you might already guess, I'm going to show it, and that's about it. So what we can go through and do is start with any one of those. I don't know why I decided to walk that way. Start with any one of our Newman projections and pinpoint it somewhere on a graph and give it some energy. What happens as we do a rotation? So if we take a look along the bottom, what we are slowly doing is rotating that methyl by 30 degrees. As we rotate it by 30 degrees, we move into a slightly different conformation, and we end up seeing different energy levels. The eclipsed conformations, you'll notice, are all with the highest energy. Taken even further, can our structure exist at a peak? No, it's a transition state on shifting between our lower energy structures. Okay? So given this information, we could go through, if I told you that the energy in a hydrogen-methyl gauche interaction was 0.9 kcals, you could go through and calculate the exact energy levels and come up with a graph very similar to this. Okay? I'm not asking you for that. What I am asking you to do is realize there is a difference in the energies and be able to qualitatively approximate where those are. Questions? Really? Okay. I guess I'll let that.
So it's a transition point, so it's not going to remain at the total eclipsed point. It'll
Sure.
keep turning.
It'll
until it
keep
gets
turning.
to
Yep.
It wants to be anti.
In a staggered conformation, and the ante is our lowest energy.
It will try to get to the lowest energy. But
Depends on temperature. So if you guys remember from 152, in theory, hopefully you all do, what we're looking at is ultimately an energy diagram. Okay? And if I wanted a reaction to go, I could increase the temperature to give my reactants enough energy to cross the activation barrier. If I'm at the 60-degree state, okay, yes, it's not as low as my completely 180, my anti-conformation. Is it possible for us to potentially prevent the molecule from getting to that anti-state? Yes. How is it possible?
Keep the temperature down.
Keep it ridiculously cold. If there's not enough thermal energy to allow for that rotation, it can't clear the activation barrier and would be stuck in that 60-degree well. How cold do we have to get? It's a little bit on the cold side. I'm not positive, but I think we're looking at 10 to 20 degrees Kelvin. Okay. That rotation really doesn't need much energy to go through and flip. All right. Are Newman projections going to show up again? Yes. Probably, arguably, my favorite way to look at Newman projections is in our cycloalkanes. So we've got a variety of cycloalkanes. As we add more carbons, we can get larger and larger ring structures. Could we get a 2-carbon cyclostructure? So what I'm saying is, can we have a carbon connected by 2 bonds?
Yes.
Yeah. What functional group is that? It's an alkene. So technically, our alkenes do get us into that cyclic structure. The chemistry changes pretty drastically. But if we think back to our formula for unsaturation, we said a pi bond was a degree of unsaturation and rings. Why? They're ultimately the same thing. Okay? So when we're looking at our rings, ultimately all we're doing is now linking that straight chain back on itself and generating these new shapes. All right? Is there any energy considerations that go into this? Say, considering hybridization, bond angles. Okay, yeah, what's that? Which one of those do you think is going to have the highest energy? What's the hybridization of every single carbon on this drawing? sp3. What bond angle do we get in an sp3 carbon? 109.5. What's the bond angle in an equilateral triangle? 60 degrees. That's an sp3 carbon. What bond angle does it want? 109.5. What did we just do?
Put the electrons closer together.
We forced that structure down on itself. Those of you with model kits, feel free to try and make a cyclopropane. If you decided to buy the cheap kits that I recommend, so I'm just going to hold this up. These general bond structures, do not try this, because you will break the model. Okay? It is that stress that the model kit will actually break.
That's how you let you know.
The other kits, these guys, you can force it down to an equilateral triangle, getting that 3 carbons. It's kind of dangerous, and it will pop and potentially spit atoms at you. All right? So just kind of watch out for that. What happens as we move up to the cyclobutane? Higher or lower in energy?
Lower.
Lower, why? That angle is increasing. It went from 60 to now 90. How about pentane?
Lower.
Even lower in energy. Hexane? Heptane.
Once it started getting increasing again.
Heptane goes up. The lowest energy you've got is cyclohexane. Cyclohexane is your ultimate structure as far as stability. We will talk about cyclohexane on Wednesday and also talk about stereochemistry from chapter 5. Okay? Both of those topics are incredibly difficult. Please review the material before lecture on Wednesday. It will help. Otherwise, you will get lost very, very fast.